Hello everyone, this is Abhishek Das. I'm a structural engineer at AECOM, and today I'll be discussing about the proof checking of composite steel I-girder bridge, which is located in the UK. I'll be talking about mainly the analysis and design aspects of the bridge. We've used the software Midas Civil for most of the design. In the next 30 to 45 minutes, I'll take you through the basic workflow, what we followed, and how the software helped us in doing that. Okay, so in today's presentation, we'll be doing the following contents. I'll be talking about the general description of the bridge, the geometry and all. And then we'll be moving on to the design actions that were considered, analysis and construction aspects, and finally the capacity checks and design. So the site location is basically the M6 to M1 link. This is the present scenario on the left hand side. We have the M6 motorway on the left, and on the right we have the A14, and from north to south we can see the M1 road, M1 motorway. Now there are some new developments in this particular area. We are going to have a lot of new structures. You can see on the right hand side there are about 10 new structures coming up, which are basically because of the congestion of traffic in the existing network. So our main focus will be bridge number 3, which you can see here. The pier locations are marked. This is a 6-span bridge. You can see the skewed piers near where the 3 is written. Okay. So this is going to be the span arrangement in more detail. There are a total of 6 spans, and then most of the piers are skewedly placed. You have piers 3, 4, 5 in the east abutment, which are having a very high skew of in the range of 60 degrees, so that they can align with the proposed M6A14 link, which is going under the bridge. And that's the elevation. This is the carriageway information. You have 6 composite steel eye girders with the bracing system in between. Overall width of the deck is 16.6 meters. The carriageway is 7.3 meter wide, which according to Eurocode will be designed with 2 notional lanes. And then you have the reinforced concrete deck slab, which is a 250 millimeter thick. Okay. The overall depth of the girders is 1.7 meters. And you have 2 verges on either side, 2 meters each. Okay. The bearing articulation of the bridge is as shown here. Pot bearings have been used, and all the bearings are having a free type of notation, which is free in translation in the lateral and the longitudinal direction, except for the central bearing for each pier. As you can see here, the central bearing for each pier has been guided with respect to the bearings on central bearing on pier number 2. Pier number 2 has fixed bearings, fixed in X, Y, and Z translation. The columns are free to sway such that they can take the temperature movements. Then the abutments and piers are reinforced concrete. Piers are basically circular in shape, which are with a torch shape, tapered. I mean, on the top they have a larger dimension and then tapered, and then finally having a dimension of 1.4 meter dia. It's supported on a pile cap with piles which are board piles. The board piles have been used here because of the depth or because of the length. Maximum length of the piles was going around 21 meters. And normally we would use CFA piles up to a depth of 12 meters because construction is very fast with CFA piles. Typical diameter of the piles used is 750 millimeters. Abutments are 1.2 meters thick. Now there was some cost comparison done just to give an idea about what different other bridge alternatives had been selected. In basically two bridge types were being looked upon. One is the ladder beam deck, which has two very deep main girders on the edges, and then in between they're supported by cross girders. So the cost was for a two-span system for either ladder deck or multi-girder deck was too high, so it was rejected. And proposed structure consists of multi-girders, and this was seen to have a much economical cost from the cost point of view, and therefore this particular option was selected. The ladder deck option was rejected also because of the aesthetics point of view. It didn't match with the other set of structures that were coming up in that particular location. This is information about the material grades used. C40 cylindrical strength for the deck piers, and for the abutments and piles 32 MPa strength of concrete was used. Structural steel work is S355 grade steel. Weathering steel was used. The benefit of weathering steel from the environment point of view is very good because it doesn't require any paints, artificial paints, which is good for the sustainability and environment. Also, it can be recycled easily and reused. A permanent formwork was used on the bridge, which is in the form of precast concrete planks. This serves in also providing some additional thickness to the existing reinforced concrete slab, thus increasing the structural strength of the composite steel girders. Okay, now I'll be talking about design actions that were considered in the checking of this bridge or the design of this bridge. Starting with the permanent actions, you have self-weight basically in the form of concrete and steel. Concrete and steel densities are shown here. Surfacing assumed was 120 millimeters, which is, you can say, the wearing course, total wearing course. There are a few pointers here about how the loads were applied in the numerical analysis software. Okay, so we use the software Midas Civil for checking of this bridge, and we applied the different loads mostly in the form of line loads, as our model that we prepared for analysis was a grillage model, and surfacing was applied as a load 2.9 kilonewtons per meter square, distributed uniformly on the carriageway. Then permanent formwork and edge cantilever formwork were similarly applied. Just to give you an idea about how these loads were applied in the software, let me take you to the model itself. Okay, so I have one of the models that we used in the analysis of this bridge. So basically loads, because of the work user interface and the ease of application of loads, we could apply loads at different locations and different patches. So As you can see here, we have the surfacing loads applied and permanent formwork distributed uniformly on different girders. Okay. Okay, then we move on to wind. So as per Eurocode 1, wind velocities were taken, basic wind velocities. So the calculation procedure is very much similar to um, what we do in all the codes. We have the pressure, wind pressure at certain location multiplied with the coefficients. So we consider two cases: wind without live load. When there is no vehicle on it, then the depth of the section is considered for wind calculation. And the other case is if we have live load, we consider the height of the live load also in picture. So these are the loads that were applied in our model, which were applied in the transverse direction throughout the length of the bridge. Then we move on to thermal actions. So as per Eurocode, we have two types of thermal actions that we can define on the structure. We have a uniform temperature action, which is maximum minimum temperature based on the shade edge temperature. We have a graph. A bridge type is a composite steel composite deck. So basically we have a type 3, type 2 type of a bridge deck, and then we have temperature difference loading, which is based on the surfacing and the reinforced concrete thickness. So there can be a nonlinear difference in the temperature on the top surface and as we go along the height of the section. So we applied these two types of loads in Midas Civil in our analysis. Then move on to traffic loads. Basically we consider three types of, or rather four types of traffic loads in this particular checking. First is a normal traffic load, which is load model 1 as per Eurocode 1, which consists of a tandem load and a UDL. It's applied on all the lanes. So the number of notional lanes is determined by the carriageway and also the shoulder. So basically if I have a carriageway of 7.3 meters and 3 meters of shoulder, then we can have 3 notional lanes in that area, and the remaining part, whatever remains, is defined as a remaining area. So the table here shows what kind of loads are applied as per Eurocode, and adjustment factors, which is similar to lane factors that we use in other standards. Then there is a general order traffic load, which consists of multiple axles. It's a special vehicle, SB 196. This is as per the UK National Annex of Eurocode. Has been considered in the checking of this bridge. The characteristic of this vehicle is that it can straddle transversely, so it can occupy more than one lane at a time. This particular vehicle is also multiplied with a dynamic amplification factor, which is for vehicles up for speeds greater than 70 kilometers per hour. Now, in our live load analysis, we combine the live load effects of both load model 3 and load model 1. So the way they are going to be placed is, again, the rules are defined in UK National Annex. So as I mentioned, this is a vehicle which can straddle in 2 lanes. So these are some rules for combination of load model 3 and load model 1. Then footway actions. So there are 2 verge on either edges of the bridge. We apply it with a footway loading of typically 5 kilonewton per meter square. Now this footway load is also applied in conjunction with load model 1. So when we combine it, we basically reduce the value, use 60% of the footway loading and combine it with load model 1. Then there is a special clause which was required to be followed in the design basis report, which is the consideration of the abnormal vehicle, category C vehicle, as per the highway manual of the UK. Now this is the vehicle that was considered. Is similar to the special vehicle, uh, the truck loading that we considered in the previous slide. Okay. Then apart from these vertical loads, horizontal loads were considered. Horizontal loads in Eurocode are braking and acceleration and centrifugal forces. Braking acceleration forces are applied as a component of load model 1 itself, applied in the horizontal direction. And since this is a curved bridge, so centrifugal forces play an important role. So for heavier vehicles, this is the formulation that is used. Normally, braking and acceleration loads applied at wherever you have the fixed bearings, which can attract the most of the horizontal forces. Then, being a steel bridge, fatigue analysis needs to be done um, for such type of bridges. So, fatigue load model, which is a special vehicle in the Eurocode, was considered. Fatigue load model 3, and this load is applied on only one lane on the bridge. Okay, now we move on to how the structure was analyzed, how the forces were applied and analyzed. So first let us look at the modeling part. The deck was modeled basically with a grillage of longitudinal and transverse elements. So being the skew angle, because the skew angle is greater than 20 degrees in the piers and also at the eastern abutment, so an orthogonal type of grillage was used. You can see on the screen the transverse elements are always perpendicular to the longitudinal elements at all location. Okay. So here the longitudinal elements mainly consist of the main girders, which are having composite section properties, and then you have the transverse elements which are representing the transverse deck behavior. Okay, the properties that we use for the transverse for the main girders is we use the effective slab from center to center distance of the main girders. Okay, we also check the effective width of the section for the stress analysis. There's the different for different types of span we have different effective width formulation, and that is used to reduce the width of the slab to be considered for stress calculation only. Then transverse deck, for calculation of transverse deck properties, we reduce the torsional stiffness of the transverse deck so that we can attract more moments on the main girders. And similarly, we can also reduce the torsional stiffness of main girders when we are designing the transverse elements, so that we can have a more we can have a safer design for the transverse direction rebars. So width of the transverse sections is equal to the center-to-center spacing of the transverse elements, and depth is equal to thickness of the slab. Then steel bracings were used, which were line elements with moment released at both ends. Steel diaphragms are used on the pier locations, which are also designed as composite properties. Okay. Then we have concrete piers and piles and abutments and pile caps, which are modeled as plate elements. Okay. So let's have a look at the model again. Okay. So in Midas, because of a more of a CAD-based interface, we could model both the substructure and superstructure together. The advantage of doing that is that we can include the same concurrent forces due to live loads and other variable loads which are coming on the superstructure. We can include those loads concurrently on the foundation as well. So it gives us some lesser conservative or more accurate analysis of the substructure. Okay. Plus, it reduces time in extraction of results because we have everything in the same model. Okay, so you see here we have the grillage model over here with the bracings modeled as X type of bracings and K type of bracings. Just to show you how the bracings are connected to the grillage deck. We've used rigid link with master node as the deck node, and which is connected rigidly to all these the bracing elements. And if I take a section out, say near the pier, okay, so we have the pier here, and just to have a look in a fleshed view. Okay, there is a pier diaphragm also, which is modeled with composite section properties. Then we have a torch pier, okay. And then the piles are also applied. The piles are also provided with soil springs, both in the horizontal and vertical directions. And then we have the bearings modeled as elastic links in the software. Elastic link is a very good feature in Midas Civil that allows us to put in different stiffnesses of the bearing and also put in guided bearings or fixed bearings. And we could also rotate the angles of the elastic link so that we get guided bearings in a particular direction. So all those things were reflected in the analysis here. These are some snapshots taken from the model. Okay, for the analysis of concrete, because it's a composite bridge, so the construction of the or the pouring of the concrete has been done at different time intervals. So the creep and shrinkage and compressive strength behavior of the concrete has also been defined in our analysis as per Eurocode 2. So basically the creep coefficient versus time, shrinkage strain versus time, and strength gain versus time was considered in the analysis. Now how the composite properties were assigned, as per Eurocode we need to keep 15% of the span on either side of the intermediate supports cracked. So most of the main girders were assigned with composite properties, except for the locations 15% of span on either side of intermediate supports where the slab was not considered, only reinforcement and steel was considered. Okay. And also the main girders are considered composite at different stages because the pouring of the deck does not happen in one go only. We pour the deck in different stages. So based on the sequence of the pouring, the beams become composite one by one. So these lines you see represent the locations where you have the uncracked and the cracked sections. Okay, so if I go back to the model, okay, we have defined reinforcement to our composite steel section. Let me show you just the section properties that we assumed in the analysis. Okay. So this is how we defined our composite section. The slab width was 2.86 meters. Okay, and these are few specification of the girders. And then we defined some reinforcement information. Okay, so these small dots here you can see are the rebars that were defined, so that we could consider these reinforcement in the cracked location near the supports. Okay, so substructure and foundation modeled as line elements for piers and piles and plate elements for the abutments and pile caps. Point spring supports in Midas Civil were used to define the vertical and horizontal stiffness of the soil to consider soil structure interaction. Now we'll talk about the construction sequence of this bridge. Okay, the main part of the construction sequence was to decide the pouring sequence, how the deck was to be poured, because the bridge is so skewed, especially in the eastern side. It was critical to have a very good pouring sequence so that we don't have any uplift in any of the bearings, or we don't have excessive deformations in the steel girders. So let us look at how the pouring was done in this particular uh, bridge. Okay. So the basic stage of construction was all steel girders were first launched. So the launching and was also done in a sequence from one end from east to the west end. Bracings, permanent bracings were uh, automatically launched as the steel girders were launched, and we had to use some temporary bracings to control the deformation. Deck is also poured in sequence. Before every deck pour, the wet concrete load was applied in the analysis, and after 6 days, the concrete was made composite. This was done in order to simulate the correct uh, load taking capability of the concrete and the correct age of concrete when the concrete was able to take the loads, and creep and shrinkage behavior was considered as per that loading. So here I have a short video just showing how the construction sequence was done. So just a little bit, this video is going a little bit fast, so I'll just pause it and then show you. So you have the steel girders first launched on one of the spans, and then slowly it goes on. Okay, and then you have the deck being poured in different stages. So starting from the east end, you have this kind of zigzag deck pouring sequence. So the support regions are left empty, okay, and they are later on filled. So that's how the construction sequence goes. To show you in the software, I have another model opened up here which just focuses on the construction of the bridge. So to give you an idea, we have say the first stage, which is you have the steel girders in. Then you have some temporary bracings in place. And another span comes into picture, and then temporary bracings. So it goes on. The way the construction stages are defined in Midas is actually helped us to reduce a lot of time involved in the analysis, and we could edit the construction stages later on very easily, because we had some we had to continuously change the construction sequence in order to come up with more optimized way of pouring the deck. So just to show you how we actually did it in the software, we have different construction stages we can model here in a very simple fashion. We just define the elements or the structural components that we want to activate in a particular stage, or we want to remove in a particular stage, deactivate. Similarly, boundaries, any particular supports we want to include, we can include in the activated part, and the loads as well, whatever loads like wet concrete loads and formwork loads. So all those can be considered very easily in the construction stages, and later on it can be edited as well. So using this tool of construction, this wizard of construction stage analysis, we could model the steel work as well as the concrete. Alright, so I'll just remove the fleshed view to make it run a little bit faster. Okay, so CS1 we had the deck wet concrete poured. And CS3 the deck becomes composite. So when it becomes composite, we activate the grillage elements as well. So transversely the deck starts participating, and so on. We have further deck coming up. Okay. Okay, and then in the last stage we have the SIDL applied in the form of surfacing. Okay. Okay, let's have a look at the deformation as well, because one of the challenges in this bridge was the excessive deformation in the steel work when the steel was being launched. So we had to provide temporary bracings accordingly to control the deformation. Okay. So construction stage model helps us to also obtain the pre-camber of the bridge, and that needs to be provided in the drawings for different load cases like self-weight and superimposed dead load and creep and shrinkage. So in different stages we were able to find out what the deformations were and where the temporary bracings need to be placed. For example, in this, especially in this skewed region, we have very high deformation. We had very high deformation in the edge girders, for which we needed to provide the bracings. Okay, so gradually we can see the deformations in the bridge, and similarly we can also when we're doing the design of the composite section, we can also incorporate the stresses, the locked in stresses from the steel only stage, and then combine it with the stage when we have the concrete in place, that is composite action. So we can look at beam diagrams also. Okay, so this is the moment distribution. It is. Okay, so and let's move on to the next aspect. Okay, where we will be talking about the design aspect of the bridge, how the bridge was designed and checked. So I'll be talking about three major parts of the design. First is the design of the main girders, composite steel girders, and then we have the design of the substructure, piers and piles, abutments, pile caps, and then design of transverse reinforcement in the deck, transverse design of the deck. Okay, so first the composite steel design, Eurocode 4 was followed for the design of composite steel girders. Major aspects of the design include the amount of longitudinal bars to be used, and depth of the girder, flange thickness, the web thickness, and also shear connectors for the longitudinal shear checks, and transverse stiffeners to be used on the web to resist the vertical shear buckling due to the vertical shear. And then SLS checks include stress limitation for reinforcement, steel and concrete. Okay. So let us go back to the analysis model, where I'll show you what are all these aspects, how they were covered in the design. Okay, so this is the full model. First of all, we generated some load combinations based on Eurocode as per UK Annex. So we had different combinations, just to go through them quickly. we have dead loads coming out from the construction stages, all the dead load locked in forces and stresses coming from the construction stages, which includes our wet concrete, steel weight, permanent formwork, and SIDL, which includes the barriers and the surfacing, and then it will be combined with live loads, different live load combinations. Okay, you can see here, just I'll open up the description. Okay, abnormal live load loading plus dead loads. Okay, then they were combined with other variable actions like wind. Okay, then SLS combinations. Okay, so different combinations were done, and then after that we looked at the forces as well, just to check whether everything is in the is according to the initial calculations that we had done by hand. So in the beam diagrams, you can look at both the forces in the steel work only section, and also in the section when the steel in the concrete becomes composite. So mainly we are interested in the for the dead loads. We have the locked in forces from the construction stages, so we can look at those as we just saw in the previous slide. We can look at we can extract forces and stresses from when the bridge was being constructed, and when the live load runs, we can look at the worst case live load positions and extract the envelope out. So there's a very good facility in the software for doing that, which we used here. We were able to extract the position of the worst case live load. Okay, so this is the worst case combination for a particular position here, and somewhere in the mid span of span 1. This is for the load case where you have both load model 3 and load model 1. Okay, so you can see how the vehicle has been positioned in alternate spans to obtain maximum sagging moment. And the influence line can also be seen in the background. So that's how this is how we could check the live load calculations with our own calculation, in-house calculations, and also you could extract the maximum envelope of these for the live load for particular girders. For example, if I activate one of the girders here, so this is how we could extract envelopes and then quickly transfer it to Excel sheets where we could apply some more calculations on it. So everything was available in the table format. Okay, so like this, and this also helped us to get the coexisting forces too. So not only the maximum or minimum forces, but also coexisting moments with maximum axial force, for instance. So that's the force part of it, and then for the design part, we used the inbuilt design wizard, and this really helped us to quicken the process of the design, because we could just use the parameters here, and they were similar to what parameters we were checking for. So we had ULS checks for bending resistance, vertical shear, stress limitation check for SLS, longitudinal shear checks. Okay. Then design material, then shear connectors. So typically we had two numbers of shear connectors applied on all the girders, except for places of high shear where we, like the pier diaphragms, where we went for 3 number of shear connectors. Tensile strength was as per the shear stud specifications, and again height and center to center distance of the shear connectors could be entered. So everything was entered in a table format and also directly applied to the model. Okay, and then we had transverse stiffener. So spacing of the transverse stiffener was also different in different parts of the section, and that was also checked and modified in some cases based on the vertical shear checks that we obtained. So for vertical shear web buckling, transverse stiffener are provided to resist that buckling. So we have transverse stiffener, typically 250 millimeter by 225 millimeter thick stiffeners were provided at different intervals, spacings. And then we have fatigue checks. So for fatigue analysis, typically for fatigue check, only one load case, that is a fatigue load model, is considered in the combination. And for the fatigue resistance check, we just, as per the Eurocode 4, we apply damage equivalence factors, which stand for the number of cycles of damage for the traffic loads applied on the bridge. And with all these parameters, Midas Civil came up with very nice tabulated tables, like bending resistance tables, which informed us about the classification of the section, the steel sections, top flange, bottom flange classification, as in the compact, non-compact, semi-compact, or class 1, 2, 3, 4. And then the moments that are being applied, because it's a proper construction, we have moments applied and to be considered in the design from both the steel structure as well as the composite structure. So we have MAD, which is the same notification used in Eurocode for the forces or moments in steel only, and MCED, which is moments in concrete only. I mean, after becoming composite, what is the additional moment that is coming into picture? And then based on the compact or non-compact section, we calculate plastic moment resistance and elastic moment resistance. And finally, if based on the compact section, we find out what is the actual moment of resistance. Okay, so all those calculations it did, which made it easier to extract the results and check quickly which part of the section was failing, and then modify or comment on those particular parts. Then similarly, vertical shear resistance checks were performed, okay, which takes into consideration the combined axial moment and shear check. Okay, so with all these, apart from all these sheets, we could also extract a detailed calculation sheet, which helped us to check whether the I mean, what are the steps of calculation, just to be sure. And also can include it in reports. So this type of sheet was generated by Midas, which provided full information on the bending resistance and shear capacities of the section. Okay. So we could easily correlate with what clause of the Eurocode was being followed in the software. Okay, and whatever was remaining, we could just do simple hand calculations to prove them. For example, for the longitudinal rebars, for for the longitudinal reverse, we do the design, we check the moment capacities, but we also check the whether the longitudinal reinforcement and the transverse reinforcement are sufficient to carry out the shear which occurs at the interface of steel and concrete and near the shear studs. So that is another check that we can do, and plus special checks at the splice zones, at the bearing location, special checks for the bracings, all those things we did using Excel sheets. A very good guidance for steel bridges that we can follow is the Steel Construction Institute manual, and also the Eurocode 4 design guide by Thomas Telford. Okay, so after the composite steel design, we could come up with a drawing table like this, which consists of information about the plates being used in the girders, and also the stiffener spacing, shear connectors used, and top flange and bottom flange welds. The pre-camber information was calculated from the construction stage analysis. So this table below with different numbers plus and minus are the pre-camber information for steel, for self-weight of steel, self-weight of concrete, SIDL, etc. Pier and pile design, because we had everything in the same model, we could extract the same combination for both our superstructure as well as substructure design. So just to give an example how we did it in the software. Again, for Eurocode 2, we have got we use the inbuilt feature for column checking. We could extract the MN interaction curves and also do a combined axial bending capacity check for columns. So I'll just select few columns here. Can we look at the checks? So we could provide column reinforcement for checking. So we provided different reinforcement and stirrups. And we obtained some information. So this is one of the preliminary models. So you can see the axial resistance check, and this shows some red zones, which means some reinforcement needs to be increased in the concrete column. Okay, so it does the full checking, stress check and also ULS check for the columns. And again, just like Eurocode 4, we were also able to cross-verify by extracting a detailed calculation report like this, which we can correlate with the code just to see if everything is going fine within the calculations or not. Okay, and then similarly, the next stage was designing the transverse reinforcement in the deck. So transverse reinforcement, because we had modeled it as a grillage of transverse and longitudinal elements, we could directly design the transverse beam itself to calculate how much reinforcement was needed in the transverse direction for the deck. But of course, we also checked it using a plate analysis later on just to be sure the stresses are coming in control, and whatever we have assumed in the grillage model is a correct assumption. So normally it will be a more conservative design through grillage model. So again, coming back to the grillage model here, if I just take one of the transverse elements, that is a starting span only. Okay, so again we provided some reinforcement just like the column design, and then selected few transverse elements, let's say, and just check them. Okay, so that's the different sections cut out on the transverse elements, transverse members, and we've got the beam moment capacity, shear capacity. Similarly, we can also obtain the serviceability information, crack fit check, crack control, and deflection control. stress control checks. So all these reports we could summarize in a table format from Midas and include it in our report. And of course, all these calculations we checked through the detailed report of Midas through different clauses of Eurocode just to cross verify. Okay, so these are different aspects that were used in the design. Okay, so with this I come to the end of the session. I hope was able to cover most of the important aspects of the design and analysis of the composite steel bridge that we did. There were also a lot of other aspects, but time permitting, I just was able to include the major ones. So thank you for your attention, and have a great day.